$24.3 billion. That is the Big Dig's total cost once interest is counted. A highway buried under Boston. 7.5 miles of roads and tunnels. The old elevated Interstate 93 disappears. A new I-90 route reaches Logan Airport below streets, rail lines, and water. The project opens traffic through its tunnels. It also opens with leaks. Then, on July 10, 2006, 26 tons of concrete ceiling panels and hardware fall inside an I-90 connector tunnel. Milena Del Valle, a passenger in the car, is killed. Her husband is driving. He escapes with minor injuries. Boston's problem begins above ground. The Central Artery opened in 1959, 6 lanes on an elevated steel highway through the center of the city. It was built for about 75,000 vehicles a day. By the early 1990s, more than 200,000 vehicles use it daily. Traffic stops for 8 to 10 hours. The accident rate runs 4 times the national urban interstate average. Deliveries arrive late. Cars idle below office windows. The waterfront sits behind concrete columns and exit ramps. The road has no room left. Entrances arrive too close together. Exit ramps cross through mainline traffic. Trucks use the same 6 lanes as airport traffic, commuters, delivery vans, and through traffic moving between New Hampshire and the South Shore. The projected answer is a new highway under the old one. Boston keeps traffic moving above. Workers build an 8 to 10 lane interstate below it. The elevated highway comes down only after the underground road can carry the city. Then Interstate 90 extends east, through South Boston, under Fort Point Channel, into the Ted Williams Tunnel beneath Boston Harbor, straight toward Logan Airport. The official name is the Central Artery/Tunnel Project. Boston calls it the Big Dig. Planning begins in 1982. The original estimate is $2.6 billion in 1982 dollars. The planned completion date is 1998. The route crosses one of the hardest places in America to build a highway. Boston is not empty ground. The city center sits on historic fill. Layers of clay, sand, buried foundations, old utility lines, and former shoreline. Above the new route stand office towers, streets, subway tunnels, rail stations, and a highway that cannot close. Workers cannot simply open a trench across downtown. They need to hold the ground in place first. The first major tool is the slurry wall. Workers cut narrow trenches through the soil. They fill each trench with bentonite slurry. The thick liquid holds the walls open while excavators go deeper. Steel reinforcement cages lower into the trench. Concrete follows from the bottom. The concrete pushes the slurry back out. A permanent wall remains. 2 walls stand on either side of the future highway. Between them, workers excavate downward. Braces hold the walls apart. Temporary deck sections carry traffic above. Then the tunnel roof goes in. Soil returns above it. The old elevated highway remains open, while the new interstate forms below. More than 26,000 linear feet of steel-reinforced slurry walls go into the project. The walls do 2 jobs. They become tunnel walls. They also keep the city from moving into the excavation. Workers monitor settlement gauges. Millimeters matter. A street surface drops too far and a water main bends. A subway tunnel shifts and the trains above it stop. A building foundation moves and the project gains another emergency repair. The route reaches South Station. 9 active railroad tracks cross overhead. Commuter trains pass through the station every day. Workers need to put an interstate tunnel beneath them without shutting down the rail yard. The answer is not a tunnel boring machine. It is a concrete box. Workers build the tunnel sections beside the tracks. Each box is up to 380 feet long. Hydraulic jacks push the finished structure through frozen ground under the railway. First, workers install hundreds of pipes into the soil. Cold brine circulates through them. The wet ground freezes into a temporary block. The rails remain level above. The jacks begin to move. A concrete tunnel slides beneath active commuter rail traffic. 1 foot, then another. The largest ground freezing operation of its kind sits below South Station. The railway continues to run. The highway advances underneath. The engineering logic works. Keep the soil stable, support the old city, move one structure at a time. But every method adds another interface. A slurry wall must meet a floor slab. A floor slab must meet a roof. A roof must meet a ventilation structure. Waterproofing must cross every joint. Drainage must carry away every drop that gets through. The Big Dig has thousands of those joints. At Fort Point Channel, Interstate 90 has to cross water. Workers cannot dig an open trench across a live channel and wait for the tide. They build 12 steel tube sections in a shipyard. Each section is longer than a football field. Each weighs about 7,500 tons. Inside are 2 traffic tubes, each wide enough for 2 lanes. The sections arrive by barge. Workers dredge a trench in the channel bottom. They lower 1 steel tube into the water. Divers and survey crews line it up with the previous section. Water leaves the joint. The seals compress. Concrete ballast locks the tube into place. Then the next section arrives, 12 times. The submerged part of the route runs for 3/4 of a mile. Above it, ships continue to cross Fort Point Channel. Below it, a new interstate highway waits for pavement, lighting, ventilation, and traffic control. The project also builds the Zakim Bridge across the Charles River, a cable-stayed bridge, 10 traffic lanes, towers rising above the river. The old elevated highway feeds into it from the south. The new roadway runs through a tunnel, then climbs back into daylight north of downtown. Workers pour foundations near the riverbank. Workers assemble steel. Workers tension cables. The bridge carries traffic while crews demolish the elevated road behind it. Boston's skyline changes section by section. The highway in the sky comes down. The Greenway takes its place. More than 300 acres of open land appear where the elevated Central Artery once stood. Downtown reconnects with the waterfront. The construction sequence achieves the visible part of the plan. The buried road is harder to see. It is also harder to finish. A normal highway has pavement, bridges, signs, and drainage. The Big Dig has all of that inside a sealed environment. Fresh air fans, exhaust fans, fire systems, pump stations, cameras, emergency phones, signal equipment, lighting, drain pipes, electrical rooms, escape passages, control rooms. Every tunnel needs all of them at once. Workers install cable trays above traffic lanes. Workers mount light fixtures. Workers hang ceiling panels below concrete roofs. Workers seal joints that may sit under hydrostatic pressure for decades. The concrete is only the shell. The operating tunnel is a machine. Then the cost starts moving. The original estimate had been built around a concept. The route changes as design advances. Environmental requirements add transit improvements and mitigation work. New connections arrive. The airport route grows. The Charles River crossing grows. The northern interchange grows. The estimate follows. $2.6 billion becomes $7.74 billion by 1992. Then $10.4 billion in 1994. Then more than $14 billion by 2000. The project has not reached final construction yet. The number keeps climbing because the work keeps changing. A redesign affects more than one wall. It changes utilities. It changes drainage. It changes excavation support. It changes the order of concrete pours. It changes traffic diversions. It changes the date when the next contractor can enter the site. Workers wait for a utility relocation. The excavation team waits for the workers. The concrete supplier waits for the excavation team. The schedule expands through every contract behind them. In 1995, the Government Accountability Office reports an $8 billion estimate. The figure excludes more than $1 billion in costs previously treated as part of the project. The planned completion date is already 2004. The original date was 1998. 6 years disappear. The city remains open during construction. That is the central difficulty. A new tunnel under empty land can use a simple sequence: clear the site, excavate, build, test, open. Boston has no empty site. Every lane closure affects a region. Every utility move crosses another utility. Every tunnel section passes below structures built in different decades from different maps. Workers open a shaft beside an active road. Workers find a pipe not shown on the drawing. The design changes. The concrete sequence changes. The cost moves again. The Big Dig becomes a project of adjustments. The engineering teams solve many of them. The underwater tubes line up. The South Station Tunnel moves under live rail traffic. The slurry walls hold. The Zakim Bridge rises. Cars begin using sections of the underground interstate in 2003. The first major roads open before the project is financially finished. Then water appears. A tunnel under a coastal city expects water pressure. It does not accept uncontrolled flow. Water enters through cracks, joints, and construction interfaces. Some leaks are small: a damp mark, a drip, a stain on concrete. Others move fast enough to force lane closures and emergency repairs. In September 2004, a leak in the I-93 North Tunnel sends water into the roadway at up to 300 gallons per minute. The tunnel closes. Federal engineers inspect the area. The Federal Highway Administration later describes the breach as isolated and linked primarily to poor construction quality in one section of the slurry wall system. An interim repair goes in. A permanent repair is designed, but a tunnel leak is not always one hole. Water follows the easiest path. It can enter at one joint, travel behind a wall, cross a construction seam, and appear somewhere else. Salt water adds another problem. It reaches steel supports, electrical hardware, and reinforcement. Workers inject grout into cracks. Workers drill through concrete. Workers install drains. Pumps carry water away. The tunnel remains open. The repair work remains too. In 2011, Mass DOT is still dealing with a Fort Point channel connection called the superplug. The structure was meant to join two tunnel sections. Settlement leaves a gap, at times measured at 6 inches. Water enters. Temporary repairs have not worked. The pumps keep running. The road carries traffic. The water keeps finding interfaces. A leak does not need to flood a tunnel to become expensive. Moisture reaches a light fixture. Corrosion starts at a fastener. A drain clogs. Salt collects in a recess. A maintenance crew closes one lane at night and removes a component built only a few years earlier. The Big Dig is complete on paper by December 2007. The maintenance program continues underneath Boston. The fatal failure begins with a ceiling. Inside the I-90 connector tunnel, concrete ceiling panels hang beneath the tunnel roof. The panels hide ducts and equipment. They are heavy. Their supports must hold the same load every hour of every day. The ceiling system uses adhesive anchors. Workers drill holes into the concrete roof. Steel anchors go into the holes. Epoxy fills the space around them. The epoxy cures. The anchors hold steel suspension hardware. The hardware holds the ceiling. The system looks fixed. But epoxy is a polymer. Under a sudden load, it behaves like a hard solid. Under a sustained load, some formulations slowly deform. Molecules move. The material stretches by fractions of a millimeter. The process is called creep. For a ceiling anchor, fractions of a millimeter become a warning. The anchor begins to pull out. In 1999, anchor displacement appears in the high-occupancy vehicle tunnel. More displacement appears in 2001. The cause is not identified as adhesive creep. The anchors remain in service. The ceiling panels keep hanging. On July 10, 2006, a Buick enters the eastbound I-90 connector near the D Street portal. It is heading toward Logan Airport. Angel Del Valle is driving. His wife, Milena, sits in the front passenger seat. At 11:01 p.m., several ceiling anchors pull free. Concrete panels and suspension hardware fall onto the car. 26 tons. Milena Del Valle is killed. Angel Del Valle escapes with minor injuries. The investigation follows the anchors upward. The National Transportation Safety Board finds that the epoxy used for the anchors had poor creep resistance. It was not capable of holding long-term tensile loads in that application. The material deforms. The anchors pull out. The ceiling falls. The NTSB also identifies failures in the design review, approval process, product information, and inspection program. The 1999 anchor movement had been visible. The tunnel did not receive the inspection system that could have found continuing movement before the collapse. Workers close sections of the tunnel. They inspect ceiling systems. They remove components. They test anchors. They replace hardware. Traffic diverts back onto surface roads and older tunnels while the inspection work moves through the system. The Big Dig had been designed to remove bottlenecks. For months, the closure creates new ones. The direct construction program ends at about $14.8 billion. Then the debt calculation arrives. In 2012, Massachusetts officials put the broader cost at nearly $24.3 billion. The difference is interest. Money already paid, money still owed. Annual debt service of roughly $550 million. The road is open. The payments continue. The comparison is visible across the Atlantic. The Channel Tunnel runs 31 miles below the English Channel. It took 6 years of construction and opened in May 1994. 2 rail tunnels, 1 service tunnel, a continuous underground link between Britain and France. The Big Dig builds less than 8 miles of urban highway. It needs construction from 1991 to 2007. The difference is not tunnel length. It is the city above the tunnel. Railways, harbor crossings, utilities, existing highways, freight routes, commuters, historic foundations, tidal water. A downtown that keeps moving during every excavation. The technical work was possible. The sequence was the problem. Build below a highway without closing it. Hold the ground. Move trains over frozen soil. Sink road tunnels into a channel. Connect every ramp. Install every system. Keep the water out. Keep the cost inside the estimate. The slurry walls stand. The underwater tubes remain in place. The Zakim Bridge carries traffic. The O'Neill Tunnel carries Interstate 93 below downtown Boston. The Ted Williams Tunnel carries I-90 traffic under Boston Harbor toward Logan Airport. Above the old highway route, people walk through the Greenway. Below it, workers inspect pumps, drains, joints, lights, anchors, and concrete. $2.6 billion planned. $14.8 billion in construction cost. $24.3 billion with interest. A highway buried under Boston. A passenger killed by a ceiling built to stay overhead. And a tunnel system still carrying water away. Subscribe for more engineering stories.